This is Mary Montgomery for assignment 4, looking at part 1, question 1, creating our new color selected 3D optimized shader. So first we have our HLSL file, where we removed the CAM data buffer, which held the view and projection matrices, and we kept the instance data buffer, which will now hold the world view projection matrix, as well as the selected color. This is also reflected in the vertex shader, which now the output position is just position times our world view projection matrix. Looking at the color selected 3D optimized header file, we are derived from the shader base class. In private, we have our constants buffer, which holds our WVP matrix and color. We have our pointer to the constant buffer. And then in our public, we have our functions. We have our color selected 3D optimized constructor, our virtual set to context function, and our send WVP color function, which we have implemented in the CPP file. We have our constructor, which creates the input layout and constant buffer. It also sends the file to our shader base class to set the file. Our destructor, which cleans up our COM object, send WVP color, which updates the sub-resource using our function parameters, and our set to context, which sets our shader to context by calling the base class set to context and set to context PSP as input layout, then also setting our constant buffer to the vertex shader. Looking at our dxapp.h, we have our shader pointer of the correct type, our color selected 3D optimized, and we initialize that in our CPP dxapp class, where we update this to be a new color selected 3D optimized, call the constructor. In draw, we do the necessary multiplication to get the worldview projection matrix to send with the color selected 3D optimized constant buffer. So we are making a yellow cube here, and we see that here. Looking at part 1, question 2, utilizing the shader class from question 1, we create a scene with 5 objects at different positions and minimize the number of matrix multiplications. So I did make changes to my color selected 3D optimized class to minimize those multiplications. We added an internal private matrix variable to store the view times projection matrix internally in the class, and I also added a set view projection function, which takes in the view and projection matrices to set our view proj matrix. This is implemented down here. We're just setting the view projection matrix to our view and projection multiplied together. And then this is also implemented in our color selected 3D optimized send WVP color function, which now we take in the world matrix and we do our internal WVP multiplication within this function before we update the sub-resource. So in our dxapp, we have all our worlds, we have our models, and we have our color selected 3D optimized shader pointer. In the dxapp.cpp, we initialize our color shader. We set it to context since that's the only shader we're using. We can set it in the initialization. We have our box model, pyramid model, our worlds, and then we can draw our scene. So first we send the view and projection matrices to get our color selected 3D optimized class to store it for multiplication just when we need it. Then we call and update the sub-resource. So we send this world view projection and color, which right now is just sending the world because the world view projection multiplication is done inside the color selected class. So we're rendering our yellow box. We set the box model to context, we render it. Since we're rendering another box, we don't have to set the box model to context again. We just use the new world, new color, render it. Now we render a pyramid, use our new world matrix. This one's hot pink. We have to set it to context since now we're rendering a pyramid rather than the box. Render another pyramid, new world, new color. No need to set it to context, just render it. Then render a box, send the world, set a color. We need to set it to context since now we're switching back to box from pyramid, render. So these are what our 5 objects look like rendered out. There they are, all using our color selected 3D optimized shader class. Looking at part 1, question 3, adding a new pre-made model, unit pyramid repeated texture that has UV coordinates that create the same texture on all 5 faces. First in model.h, we need to add this new pre-made model, our unit pyramid repeated texture. Implement that into model.cpp. Have a case for it, which calls our create unit pyramid rep texture, which is defined in our model tools.h class here, and then implemented in our model tools.cpp class here. So we're creating our unit pyramid with repeated textures. So setting up these faces was a little hard at first. All of my triangles are set up so that it's the top, bottom left, bottom right, going in our counterclockwise order. I knew the top needed the 0.5 somewhere because we were in the middle of the texture image. I definitely spent a lot of time looking at the texture image, and then eventually figured out it was 0.5, 0, 0, 1, 1, 1, and it's the same across all because all my triangles are set up the same. But then for the bottom, we don't need to render our triangles separately. We just texture the whole bottom square and can use our square alignment test image. Then in dxapp.cpp, we make sure to load the correct texture file, our alignment test.tga file. We create our pyramid model, and then we render it out. We didn't have to change anything from the demo. We're just rendering this pyramid that should now have our alignment test texture on all sides. And there it is. Looking at part 1, question 4, adding a new pre-made model, unit box 6-face texture with UV coordinates such that a single texture wraps around all 6 faces. So first in our model.h, we create our new pre-made model, unit box 6-face texture. We create a case for it in our model.cpp, which calls our create unit box 6-face texture function, which is declared in model tools.h, and which we implement in model tools.cpp. So the only difference between this code and the repeated texture code is the UV coordinates in the pvert set function. So first I just kind of drew out the cube face texture image and figured out the actual coordinates of each face, which I have written to help me when placing them in the actual set functions. So I kind of just tried to visualize the unit box in space and try to match up where I thought the vertices would line up to this 2D texture image file. So with some guessing and checking, I eventually figured out all the faces, matching them up. And then in our dxapp.cpp file, we make sure we're loading in the correct texture file. I loaded in the cube faces Jaina one because it has those helpful little colors of like what face should be connected where. Then we create our unit box 6-face texture model, and everything else is the same. We're just rendering out a cube, our unit box. And so we can look. And here's our unit box. So I like these little colors, good indication that I'm doing things right. And there's our box. Looking at part 1, question 5, create the shader texture class to encapsulate the work needed to set up and control texture.hlsl. This is our texture.hlsl file, and here's our shader texture.h class. So we derive from the shader base class again, and we have our constructor, destructor, our virtual set to context, and other functions, which I'll go over in the CPP file. And then in private, we have our constant buffers gotten from our texture.hlsl file. So we have our cam data and instance data constant buffers. In our CPP class, we have our constructor, set the shader to be our texture.hlsl file, and then initialize the input layout and constant buffers. We have our destructor, release and delete our COM objects. We have our set to context, which calls our shader base class functions, set the VSPS input layouts, and then set the shader texture constant buffers, our 2 constant buffers. Our set texture resource and sampler, it takes texture as a parameter. So I'm calling the set to context with this texture, utilizing this texture.cpp function here, where we set the shader resource and set samplers to our pixel shader. Send cam matrices updates our view projection matrix constant buffer, update the sub resource. Our send world takes in the world matrix parameter, creates our constant buffer, and updates the sub-resource. dxapp.h, we create our world matrices, create our models, create our texture shader, now using our new shader texture class. dxapp.cpp, first we make our new shader texture objects. We could remove a bunch of code here that's part of our shader base class, so we just create our shader texture object, and we can set that to context since we're only using that shader texture shader class. Here we can load in the textures, preload them before we set any of them to context. We're not sending them yet, that's all done in the draw stage, but we can preload our create texture, our cube base texture, our alignment test texture. We can also preload the models, but wait to send them. So we have our box repeated model, our 6-face texture, our pyramid repeated texture. Then we initialize our world matrices, and then our draw scene. So we are utilizing our shader texture class, so we update the constant buffers. This cam matrices constant buffer only needs to be updated once, since those matrices don't change, but we do need to send a new world matrix to update the sub-resource with each new object. So our first object, we send a world. Since all of our textures and models are preloaded, we can simply set them to context when they're needed. So first we're setting our create texture to context, then we're setting our box repeated model to context, and we're rendering out our repeated box model with the create texture object. Object 2, our 6-face textured unit box. So first we send the new world to the shader texture constant buffer here, and then we can set our 6-face texture to context and our p unique box model to context, since those are both again preloaded. Then we just render it out. Object 3, repeated alignment test texture unit pyramid. So first we send the world, update the world constant buffer. Then we set the texture to context, our alignment test texture, set to context, and then set our pyramid repeat model to context. Again, those are both preloaded, so we can just set them to context in draw, and then we render out our pyramid model. And what that looks like is our 3 separate models with their unique textures, all preloaded and just set to context in the draw scene. Looking at further work question 1, setting the model to be unit box and applying our different textures with various combinations of the filter address modes and seeing what happens. So first off, our unit box model is created without any associated UV coordinates, meaning its vertices have no position data on the texture. Our unit cube also does not have duplicate vertices to accommodate for the UV texture mapping needed on a vertice to store multiple face texture data. Since our set function has a default UV value of 0, 0, our simple unit box model still works to apply the texture at 0, 0 to the vertices of our unit box. This creates just a flat colored box because we're only using the texture at the UV 0, 0 coordinate, not mapping to the UV in any way. So my demo 1 had the cube face texture, used the point filter, and clamped addressing. So point filter uses the nearest neighbor to determine color. Since we're looking at the 0, 0 spot in the cube filter texture, we're looking at a white texel, so our unit box is an all white box. Since every vertex is set to this white color, all of our neighbors are white. Clamping, if we have anything outside of our range, we're just clamping to our white texel, so we just get an all white box. Demo 2, I use the cube faces texture again, linear filter, interpolation, wrap addressing. Linear filter, regardless of the texture size, under magnification will look blurry. However, we are not seeing this since, again, we're only using the 0, 0 spot in the cube filter texture, which is just white, so our box is all white since every vertex is white, and interpolated white gives us white. I won't even waste the time playing that. All demos simply give us a solid colored unit box because we're only using the texel at 0, 0 in the texture at every vertex of our cube. So no matter the point or linear filter, or apply clamp, wrap, mirror, border, addressing, our cube always looks the same. Since the 0, 0 texel at cube faces is white, we get a white box. 0, 0 texel at create faces is light brown, so we get a light brown box. The 0, 0 texel at X512 is red, so we get a red box. We can see these real quick. Addressing would usually determine how to repeat the texture, since our UV coordinates are always between 0 and 1. Any range outside needs that protocol for how to apply texture. Wrap will cycle the texture anytime you go out of the UV range. Mirror will bounce back and forth when going outside the UV range, so the texture will map 0, 1, then will map 1, 0, then back to 0, 1, etc. Border will give you nothing outside of the 0, 1 range, just black nothingness. And clamp, which outside of 0, 1, you clamp the edges to the last values in that 0, 1 range. However, we didn't really see any of this because we were only looking at the 0, 0 texel, so we're just getting solid colors. Looking at further work question 2, performance test. So first we are setting our sync in dxapp.h to 0 for no sync. Then I am just going off of your demo, creating the world matrix array. I have our static constant for side count and separation to create this performance structure. We have our models, our texture shader. So I'm using the same code as in part 1, question 5. So in dxapp.cpp, we initialize our world matrix array the same way you did it in the demo. I backed up the camera because I couldn't see most of my structure. And then in our draw scene, I have 3 different loops, which are just rendering out my 3 different objects from question 5. So this is rendering out the box repeated model with the crate texture. This is modeling out the 6-base texture unit box. And this is rendering out the alignment test texture pyramid. We're doing extra work with all of these. We're setting the camera matrix every time, setting the world, setting the context. With each of them, when we run it, usually we're looking at like a 60 FPS. Running this, we are down to like a 10 to 13 FPS. And then we can just look at the CPU usage report, which I ran already, and I can see what changes when I take, the unnecessary send camera matrices out and things like that, but this is helpful to see. So that is looking at my performance.